Все, полетели на ракете. So, let me start once again, sorry. So we will talk about dynamical systems and its connections with other branches of mathematics. Today's lecture is an introductory one, when I will try just to make a kind of a teaser for you discussing what it can be about, how the study of dynamics can look like, and why do we do that. And then the first part of the course is kind of fixed. There is a syllabus which is already determined. I will make a teaser today. And the second part is up to you. You will decide what you want to listen about. I will give you some choice, and you will decide which parts are more interesting, which parts you prefer to study by yourself and make presentations here in the auditory, and which parts we are skipping and wait for the next moment to study them. So concerning the parts that we are planning to cover, today I will talk about dynamical systems in general, and starting from the next week, I would like to introduce you to the word of geodesic flow. On surface. And in order to do that, I think we need to cover some possible holes in your background that may concern the geodesics and in general some hyperbolic geometry. So don't be stressed next time if you get a feeling that the class is not about dynamics but more about geometry. It's not the case. Just I need to be sure that everybody has a similar level of understanding of how do things work in a hyperbolic geometry, and then we will be able to define the geodesic flow and use it as a kind of a baby example. So we will examine general dynamical techniques and notions with respect to this dynamical system that looks rather elementary and natural. And it will take us some time, exactly because first we will study a little bit what hyperbolic geometry is, and maybe some aspects of topology, since I'm supposed to study the flow on the surface. And then this is what is necessarily fixed. Typically, I like to introduce the students to the notion of homogeneous dynamics, partly because it's very fashionable now, mainly not just as a separate subject, but in applications to the questions in number theory and in geometry. So I think it's quite cool to see that dynamics can be useful for other mathematicians as well. And that's why we typically study that. And then we have a lot of freedom. So one option is to go to Teichmüller dynamics. That's what I'm doing as my main subject, so I like it a lot. But you are not obliged to share my tastes. This will be partly similar to what we do here, especially in the first part, but will require a little bit more involved attitude toward the topology. There is an interplay with geometry in moduli spaces, where Sergei Konstantinovich is an expert, and the ergodic theory. So this is one option. Then another option is to go more to the analysis, kind of to touch a little bit the connection between dynamics and probability and analysis. And in this case, we will study what transfer operator is. Transfer operator. And how do the knowledge of functional analysis and some probability techniques can help us to solve purely dynamical questions. Another option is to go to a discrete world, so we may study symbolic dynamics instead. These two options are in some sense orthogonal, because in this case you concentrate more on a very discrete models, and you study kind of combinatorics much more than some analytical part. So this is another option, and the sixth option is to go into ergodic theory of Markov shifts. So I think you will be able to make a kind of knowledgeable choice once we finish the first block, because I will introduce you to all the notions that I mentioned here, and you will be able to choose what you prefer. There is one more important question, the question about grading. This I will discuss in more details next time, because if we have some more people in the auditory, they can be stressed about that as well. But normally, the grade is comprised of two parts. One part is given for oral presentation. So you choose a topic, or I help you to choose one that you like. You read a paper and explain it to the auditory. So it's kind of a small block of your separate research, not necessarily with some independent results, but you study the paper by yourself. And then the second part, we will give you some lists of problems, not after each lecture, but maybe after each two or something like that, after each block. And you can solve the problems, and each list of problems will weight around 2 points. And normally we have like 4 or 5 lists. So in general, if for some reasons you don't like to make oral presentations, you can just report the solutions for these problems. Or on the opposite, with oral presentation, normally you have up to 7 for oral presentation. And then the rest of points is formed by homeworks. But as you can see, you are not obliged to solve every problem in every list. It's enough to get familiar with any of them, or to go deep into 1 or 2 teams instead of studying the whole list of problems. So it's up to you. If you like to make oral presentations, you do that and then solve some problems to get the perfect mark. Otherwise, you concentrate on the homeworks, and then you skip the oral presentation. Okay, so now it's time probably to say something meaningful, and I'm going to start from the definition of the subject that we are interested in. Informally, what does it mean to study the dynamical system? It means that we try to look at some long-term behavior of evolving system. So, behavior of evolving system. And in general, the system can be whatever system you can imagine. So sometimes you can look at some physical problems. And for instance, you can see some solar system as a very typical example of a dynamical system. On the other hand, if you try to model some biological process or the process in economics, you can easily get a dynamical system as well. So the subject is extremely broad, and can be both very abstract and very applied. Historically, indeed, the solar system was the first dynamical system people get interested in. Solar system. And they tried to study the questions of stability and evolution. And the first attempts of the successful answers on some of the questions appeared in this context are from the end of the 19th century. What are the typical questions that interest the dynamists? They are related to the very important notion in dynamical systems, the notion of the orbit. And the name exactly comes from the fact that the science originated from the study of solar system. So the orbit can be seen as the evolution of a particular state. So when we go to the typical questions, normally what we are interested in. Sometimes we work as psychologists, so we are following the properties of individual orbits. For instance, you are playing billiard, you took a particular point, and you start to follow this point, and you would like to know how the orbit may look like. This is how do psychologists work, and this is sometimes the way how do we think about dynamical systems. Sometimes we are interested in a particular properties. Especially we like the periodicity of orbits or their ability to be everywhere dense. It's kind of two polar version of the behavior. Maybe there is something in between, then we are interested how it can be characterized. Then we also like to study the statistical problems of the orbits and to answer the question which behavior is typical. At this moment we turn to kind of a sociological approach. So what does it mean? It means that, say, we are not interested in the properties of one particular orbit, but we ask ourselves, is it expectable to find the periodic orbits? How widespread they are? What is the more typical behavior, to be everywhere dense or to be periodic? Or is it true that the periodic orbits are everywhere dense among all the orbits and things like that? So in this case, it looks a little bit more like a probability theory, even if we do not add any randomness at this moment. So it's like we don't want to know about each person, but we want to know about their typical behavior. Then, since we mentioned the probability, we may add the random aspect, so randomness versus determinism. Sometimes we may study random dynamical systems. For instance, it's the case, from this point of view, stochastic processes are a good example of a dynamical system as well, but sometimes we live in a very determined world. So this is another part. Then there is a question of entropy. We want to measure the entropy of the system we deal with, and we want to answer the question of how chaotic the behavior of our system can be, or how predictable it is. And then there is also a question of stability. Stability under the perturbations. And this question can be asked both for individual orbits and for some patterns. So this is more or less a list of questions that we are going to ask ourselves. And so our plan for the whole course is the following. We will take some dynamical systems, try to define them in the most rigorous and accurate way. Then we will examine them from this list, asking ourselves what's going on with our particular dynamical system. And then we will think how can we apply the knowledge we got to some other branches of mathematics. Maybe we get some information that is useful for somebody else. Sometimes it will be the case. So we're going to start today from some examples that look more or less natural. So first I suggest you to study the discrete case. In this case it's easier to give all the definitions. So the discrete case works as follows. We take some space. Of course we don't want it to be empty. And we have a map that acts on this space. And then we are allowed to iterate this map. So we have a composition. And we do this. And if f is invertible, then these iterates, they form a group. Otherwise it's a semi-group. Now, very typically, we need to add some information about this space. So we like the case when, for instance, we get a measurable space. This is one option. So it's a measurable space. So we are equipped with a measure, and in this case, we want that f preserves this measure. So we have a couple of the measurable space and measure preserving map. One option is when we have a topological space. So we know who is open and who is closed. And in such a case, we need to add some condition on f. For instance, we ask that it's continuous. We can also think about the situation when we live at a smooth manifold. And in such a case, we want also f to preserve its structure, so it's some differentiable map. And so on. Of course, none of these things is compulsory. So if you prefer, you may think about some dynamical systems in a very abstract setup. But since, as I told you, we like to think about the problems that have some sense, not only for us, for dynamists, but also for somebody else, we very rarely live in such a situation. We usually equip X with some additional structure on it, because the most meaningful spaces, they carry some additional structures. So what is the difference if we switch to the continuous situation? What changes in this case? Okay, then we cannot iterate like here. So instead of one map, we need to consider a one parameter family of maps. So we still have X, and we add one parameter family of maps ft x to x, and it can be either a group or a semi-group as usual, but what we want is that if the time t plus s passed, then it's the same thing as to say that first the time t passed and then the time s passed. And at the point 0 we have just a trivial map. So we may define the flow, and depending on the fact if our time is running only to the future or also to the past, it can be a flow or a semi-flow. And then we still have the same notion in both cases of the orbits, periodicity, and there is one more important notion, the notion of conjugacy. It's a way to say that two systems, despite of rather different appearance, are more or less the same. So that there is a map that allows us to make another system from the one we started with. Of course, it makes sense only if we are able to prove something interesting about one system, and then it allows us to say also something meaningful about another one. So I'm going to tell you now about some examples. I hope it will be more illustrative than some abstract setups that we already discussed. So let me start. Example number 1 is probably the most influential dynamical system in the world, which is called the rotation of the circle. And you know it since you were at the first year of the university and you studied the calculus class, its properties. So we take a circle, identifying 0 and 1. And if we add modulus 1, then we make it an abelian group. So we can keep it with a distance, which is a minimum among the modulus of x minus y and 1 minus the same quantity. And the Lebesgue measure is induced from S1. And we have the map that works as follows. We fix some real number, and we add this real number to x, and then we add modulus 1. Then what can we say? If we fix this alpha and consider R alpha varying alpha from 0 to 1, then we get a group with a composition as a group operator. So it's commutative group. Commutative group. With composition as a group operator. So we know how to consider the composition R alpha, R beta. It's like R gamma, where alpha plus beta is gamma modulus 1. So it's an isometry. I mean, it preserves the distance that we defined here, right? Moreover, we know that it preserves the Lebesgue measure. And then it fits in this framework that we discussed there. And moreover, we already know all the basic dynamical properties. Because you can answer me the question, if alpha is rational, then we know everything about its orbits, right? They all are periodic. So RQ alpha is D, so it's periodic. And then if we take an irrational number, we also know everything about its dynamical properties, because we know that our system is minimal. System is minimal. Minimality here means that all orbits are everywhere dense, right? I hope it's not a surprise for you. You still remember what you did at the first year. So then, in reality, we have even more. Because to prove this, we did not need any notion of the Lebesgue measure, but we are able to prove that any measurable R alpha invariant set has either the measure 0 or the full measure. So any measurable R alpha invariant set is either of 0 or full measure. You see that, right? Because basically the only closed non-empty subset, which is R alpha invariant, is the whole S1. So, and then if we have this, there is a special word for it in dynamical systems. The word is ergodicity. And we know that our map is not only minimal, but it's also ergodic. So this is the first example when we were able to answer the questions that we discussed before. And this is how more or less our research will look like. We will take different systems and try to understand the answers on these questions. Actually, the circle rotations can be considered as a particular example of an important class which is of dynamical systems, which is called group translations. So if we have a group G, we may consider LH G G, LH G H G, or RH G G, RH G is GH. So if our group is commutative, then this LH and RH, they will coincide. Otherwise, there are two different maps that require different study. Okay, this was our first and the most elementary example. now we are ready to switch to the next one, but before I will comment a little bit on this thing. So as I told you, one of the options for us is to study Teichmüller dynamics. So Teichmüller dynamics basically generalizes what's going on here. We will consider a map that can be seen as a generalization of this map. And the second comment is that I told you that this is the most powerful dynamical system in the history of dynamics, probably up to now, because it initiated several different directions. On the one hand, as I said, there is a Teichmüller dynamics that grew up from there. At the same time, it was also the basis of famous KEM theory, Kolmogorov-Arnold-Moser. So this was the first example that laid on the basis of this theory. So somehow such a small example, very clear already for high school students, in reality influenced mathematics of the 20th and 21st century already a lot. So now the next example, which is also very important, and we will remember it later when we will study the geodesic flow, is the expanding endomorphism of the circle. So this is our example number 2. And it works like that. So we take an integer, and we want it to be different from 1 and 0. And we consider a map from S1 to S1. This is our favorite X for today's lecture. That works very simply. There we used to add, now we want to multiply. It's like in a primary school. First you study this addition and then you switch to multiplication. So that's what we do here. Just we always add this modulus 1. So apparently this map is non-invertible, forms a non-invertible group of endomorphisms of S1. So every point has m preimages. So xm expands the arc's length. It's not isometry anymore. Now we have expansion, right? So it expands the arc's length and the distances between the nearby points, where you don't need to apply this modulus 1, by a factor of m. So if you take two very nearby close points, then you will multiply by m. Let us write it down. EMX, EMY is MDXY. So a map of a metric space that expands the distances between the nearby points by a factor of at least some number greater than 1, it's an expanding map. So that's why we use the word expanding, because that's exactly what it means to be expansive. Expanding, sorry, not expansive. So then at the same time, our map preserves Lebesgue measure in the following sense. Let's So if we take some subset in S1, which is measurable, then lambda, the measure, the Lebesgue measure of its preimage, is equal to the measure of the set itself. It's very important. That's exactly what it means to be measure preserving, to the measure to be invariant with respect to this map. because it's a little bit counterintuitive. You expect that there should be the equal measure for the set and its image, but that's not what you want. You want to be the same, the measure of the set and the measure of its pre-image. And it's critically important. So, in particular, if you take the measure of the image, if it was small enough, you're gonna have a multiplication. So it's not true that you can mess up with it. You need to decide at the very first moment what does it mean for you, for the measure to be invariant, and we stick to this definition when we deal with the pre-images and not with images. So later we're gonna see that EM is moreover ergodic with respect to Lebesgue measure. So that any subset which is invariant, it has necessarily zero or full Lebesgue measure. Now we will construct the connection between our EM and another famous dynamical system, which is partly related to the number theorem. So let us do that. So we will construct the semi-conjugacy. Between another famous and natural dynamical system and our EM. So we take the set of sequences we take the numbers from 0 to m minus 1. For simplicity, for a moment, you can take m equal to 2 and just build the numbers with 0 and 1 to make it more easy to imagine. And then we define one of the most influensive set, which is a map, which is called a shift. So it does the following thing. It takes an element from here, discards the first element, and then moves the rest to the right. So, I mean, we change the numeration. We forget the first element, and then the person who was the second becomes the first, the person who was the third becomes the second, and so on and so forth. So that's what it does. This is called the shift. Of course, you can do it in the opposite direction as well, if you prefer. So it's called right-sided or left-sided shifts, but we will always think in one direction. Since we write from the left to right, it's easier to forget the guy who is on the left. And that's what we will do. So it takes the sequence x1, x2, etc., and it discards x1 and continues the rest starting from x2. Now, let us consider the following notion, which is called base M expansion. You definitely studied it when at school. You studied different counting systems. So you take a point from 0 to 1, and you consider xi, mi. So you represent it as a sum of integers divided on mi in some power. So then you get a presentation of it like that. Typically, that's what we get when we live in decimal system. We take m equal to 10, but I hope that you are familiar with other options as well. In this case, you know that this presentation is not necessarily unique, but still. And so then you may build a map from your set of sequences to 0, 1. Because with each sequence, you can associate the number that you construct in this way. Gluing 0 and 1, we can consider phi as a map into S1. So instead of taking this, we can replace it by S1 if we glue 0 and 1. So now what can we do? What can we say about this map? It's a surjective map. It's a surjective map. And it's actually one-to-one, except some countable number of sequences. Because as you know, this presentation is not unique, but the exceptions you can control who they are, right? So then you can see, moreover, that if you take a number x1, x2, etc., and then you apply your EM, so it means to multiply on M and then go back to the circle. It's nothing different than to say that what you get is x2, x3, etc., right? So you start from x, and when you apply EM, what you do gives you the same thing as if you would use a shift. So in reality, you may say that the composition of phi with a shift is nothing else than the composition of EM with phi. So phi is a semi-conjugacy from sigma to EM. Thus, we know that this dynamical systems that we discussed is very close to one of the most natural dynamical systems that exist, the shift map. How can we use that? For example, we may study the periodic points and apply the knowledge that we have to get the information for the periodic points of EM. Say you take xi, that is a sequence, and you know that it is periodic for sigma. For sigma with period k. So then it is the same thing as to say that it's a periodic sequence with period k. So it means that what you know is that x k plus I is equal to xi, right? But then for any I. But then if you know that, then it means that you can count the number of periodic points for sigma. Number of periodic points for sigma. Because all the diversification you may have, it only lives on the interval of the length k, and you may choose all the options only between 0, 1, etc., m minus 1. So there are not so many variants what you can get. But then it means that you can apply this knowledge to the study of periodic points of this EM. So if x from S1 is periodic for EM with period k, then it's the same thing as to say that x has a base M expansion which is periodic with period k. But then it means that you can count the number of periodic points for EM. So number of periodic points is nothing else but m in power k minus 1. This is the first example when how can we use the fact that we know that some systems are conjugated or semi-conjugated. So we can sometimes replace the study, for instance, of periodic points of one system by a similar study of the second one. So what we study here is something which is called the symbolic presentation, because you have a fixed number of symbols and you coded the system that you started with with this finite number of symbols and sequences made by this finite number of symbols, and then with a shift defined on these sequences. That's what symbolic dynamics does, typically. If you have some abstract systems, you choose a coding that would allow you to present the system as a shift on some particular set, and then you study the dynamical properties of this shift. So as I said, one of the options is to go into the symbolic dynamics as a part of our course. So that's what we're gonna do in this situation. Let us continue to study this system. So let me take the set of all sequences that are built with 0, etc., m-1 elements. And let's say that it will be a set of all finite sequences. We will exclude infinite ones. So a set of subset of 0, 1 of the interval is dense if and only if for any element of this set Fm, we can say that any word occurs at the beginning of the base M expansion of some element. Right? Because what does it mean to be dense? It means that you take a point, you choose a neighborhood, and you want me to enter this neighborhood. But what does it mean in the language of symbolic dynamics? It means that in order to fix the neighborhood, you choose some amount of first symbols in your word. And then I need to find a word such that this collection of the first symbols will be the start of this word. That's exactly what we wrote here. So we do this. It's m n power k minus 1. So then it means that if we apply this idea, we will see that the set of periodic points is dense in S1. So the orbit of some point is dense of some point which we can code by this collection of x1, x2, etc. is dense in S1. It happens if and only if every sequence from Fm appears somewhere in the sequence xi. So since Fm is countable, we can construct such a point that it would be true just by concatenations of all the sequences. Right? So then we can see the following thing, that actually what we can do is what I already said, that we can replace the study of Em by the study of sigma, and the description of sigma will be identified by the partition of the original intervals on the parts such that they correspond to the same choice of letters in the sigma. So once you choose the first number after 0, after the point, then you chose a particular part of the interval 0, 1. You choose the second, you choose even a smaller part of this partition. You choose the third, you choose even a smaller one, and so on and so forth. So what you get is a partition, and you may study the ergodic properties of the maps that take small parts of the partition to the whole space where it is defined. And that's what I'm supposed to cover if you choose the part of ergodic theory of Markov maps. This is a typical example of Markov partition, a map that corresponds to it, and that's what we are supposed to study, the ergodic properties of maps of this type. So, okay, this was the example number 2. I have many others, so let's study the third one. So, this is also something that you definitely have already seen, which is called the Gauss transformation. This is example number 3. So this is what we have, 0, 1, 0, 1. Phi of x is 1 over x minus the integer part of it. This is just the integer part. And you do it every time when you leave between 0 and 1. And in 0 you say that it's just 0. So this is our map. And what it does, it maps each small part between n, 1 over n plus 1 and 1 over n continuously and monotonically. It maps onto 0, 1. So at every point that looks like 1 over n is a point of discontinuity. This is another example of the maps such that we're going to study their ergodic properties. But if we want to understand the ergodic properties, it means that we want to understand either this map is ergodic or not, and we can even increase the degree of how mixing it is. Mixing means that you have a space where your map is defined, and you want to understand how often do you visit some parts of this set. And if the regularity of your visits depend on the position of this part or just on its sides, and so on. So if we want to study this kind of stuff, first we need to take some ergodic measure. We need to understand how it looks like. And in this case, if you look properly, you will see that Lebesgue measure, the standard one, does not work very well. So you need to change somehow the density of your measure. You need to define some measure which is equivalent to Lebesgue one, but has a different invariant measure in a way that it would be a probability measure for invariant with such a map. So we are going to construct the invariant measure. And this is another thing that you typically need to do once you are given a dynamical system. You need to understand who is invariant measure for this map. And by invariant, as I already told you, the measure such that the measure of the preimage of measurable set coincides with the measure of the set itself. So if we take a measurable set, okay, we know, we are very educated, took a course of the measure theory, so we know that measurable sets can be modeled by intervals. So we need to be able to measure such an intervals, and the measure of such an A is nothing else as 1 over log 2 integral dx x plus 1. So if you compute it, it's a log 1 plus b 1 plus a. So the bad news are that if you want to study dynamical systems, you should not be afraid of integrals. Sometimes you will need to do such a computation. So let me prove this to show you how it can be done in general. In order to prove it, we need to check that this measure is good enough. We will cheat a little bit. We will not calculate the measure, but we will use the answer that I already gave you to check that it's a good measure. So in order to do that, we need to understand how the preimage of this interval may look like. So it contains of infinitely many, the preimage of AB. So it's infinitely many intervals. And each, what does it mean? Because in each 1 n plus 1, 1 over n, there is a 1 over n plus b, 1 over n plus a. And this is the guy that goes here when we apply our map. So we need first to compute the measure of this person. Let's do that. So we say that there is a mu of the preimage of AB. So it's a measure of the union of these intervals but then what it means, it's 1 over log 2 of sum of logs n plus 1 plus a over n plus a, n plus b, n plus b plus 1. And now it remains to apply the fact that the log of the product is the sum of two logs and the log of the fraction is the difference between two logs. So you will kill all the intermediate members and you will get the measure of the whole interval. And once again, you see that the definitions that could be rather more intuitive will not work. Measure does not satisfy the condition that the measure of the image is equal to the measure of the original set. And this Gauss map you probably studied already if you saw the continued fractions. So what does it mean, the continued fraction? I recall you. A1, A2, etc. So you can see that your x is 1 over x plus phi at x. So you can see your x, you can continue this, and you can see your x as a continued fraction like that, with phi of x at the very end. So any rational number is uniquely represented by a continued fraction, and for a rational number you can find the members of this AI using the procedure we have. So your AI is the integer part of this. And the converse is also true. So if you have a set of Bn such that you have a convergence to some point, then you know how the application of phi to B look like. It will give you exactly this B. So the continued fraction algorithm conjugates the Gauss transformation and the shift. Exactly the same maps that we studied before. So you have a conjugation between the Gauss transformation and the shift on the space of finite or infinite integer valued sequences. Okay, I think we can make a small break here because it looks like it's a time to, right? Или еще рано? Пора уже, наверное. Okay, then I can do more. Then we will study one more example and then make a break. Hyperbolic total automorphism is my next example. So let me give you a very particular example. I mean, it's still the class of dynamical systems, but I'm gonna speak about just one particular representative. So I take A, which is 2, 1, 1, 1. It's a matrix. And this matrix will act on R2, so it will lead us to R2 once again. I hope you know how to compute the eigenvalues of this matrix. So you will see that they are irrational. And lambda 1 is given by this formula, so it's greater than 1. But the determinant of this matrix is 1, so lambda 2 is just 1 over lambda 1, so it's smaller than 1. And what can we see, how it acts on R2? Then we can see that it expands by the factor of lambda in the direction of the eigenvector that corresponds to this eigenvalue, and then it contracts on lambda 2 times in the direction that corresponds to this eigenvalue. So that's the picture that we exactly will see for the geodesic flow on the surfaces. It will do a similar thing, and that's why the word hyperbolic lives here. And moreover, there is a branch of dynamical systems which is called hyperbolic dynamical systems study. So it's dedicated to the systems that have a similar behavior. What does it mean to have similar behavior? So it's expanding in direction of V lambda given by this, and contracting in direction of V1 over lambda given by this. Since A has integer entries, then it preserves Z2 as a lattice, right? So we can say that we can consider a map not on R2, but on a factor of R2 over Z2, which is T2, a two-dimensional torus. So it induces a map on T2 to T2. And we can say that T2 is a commutative group, and A is its automorphism. It defines its automorphisms. So now we can even answer the questions about our favorite one, about the periodic points. What are the periodic points of such an action? They're given by the points with rational coordinates, obviously, because the map has integer coefficients. So in order to be periodic, it should be a solution of the equation with rational linear equation with integer coefficients. So not many variants, rational coordinates. So if we take the lines that are parallel to V lambda, here on R2 we had an expanding map. And what do we have here once we project to T2? We get the family of parallel lines on T2, right? And this family we can divide by, denote by WU. So it's a family of parallel lines. I will mark that they are associated with V lambda. And we will call it an unstable manifold. Why is it unstable? Because when you take 2 points that belong to it and you apply your map, the distance among these 2 points increases. So your trajectories have a feature to go farther and farther from each other. And then what you get is that this WU defines a partition of T2. And this gives you so-called unstable foliation. In order to visualize it, you can think about toys that you maybe have had, probably you had, because typically girls had it, boys more rarely. You remember there was such a thing that was very colorful, like of rainbow colors, and it could make steps on the stairs. The name could be different, but it looked always like it had such a shape, was not very big typically, and was very colored. So that's what you have here, because that's what defines a foliation. If you look locally, it's just a partition by parallel planes, but then it forms the whole T2. And if you choose a direction in a way that it's parallel to this guy, then you will have unstable foliation. But then you could do a different thing. Moreover, this unstable foliation, it's invariant under the action of A, in a sense that you could alternate their order. And each line in WU is expanded in a lambda times. Similarly, you could define a stable foliation. You just need to repeat the whole procedure, starting from the set of parallel planes that are parallel to this guy. So you choose a different angle for this person that could make steps on the stairs. And since their slopes are irrational, each of the stable unstable manifold is dense. They both dense in T2. Okay, so this can be actually generalized. We could replace A by whatever matrix with integer coefficients and the same property, that one eigenvalue is greater than 1 and 1 is smaller than 1. You had a little bit similar experience in differential equation course. You remember when you had to classify the orbits of your corresponding dynamical system, actually using the matrix of the linearization of your system, and you were able to draw a phase portrait. That's more or less what we do here, but we add a little bit of topology while projecting. So this gives you an automorphism, and it is a very important example, because when we're gonna study similar properties of the geodesic flow, it will also have stable and unstable manifolds, and it can be not so easy to imagine it, but if you have this example in mind, it will be much more illustrative. So now the next example, we still have a bit more time. Actually, I already mentioned it. We can take... we can take the differential equations on board and look at the dynamical systems defined by the differential equations. In some sense, the purpose of today's lecture is, on the one hand, to convince you that you already know what dynamics is, that you studied many things that are pretty much related to it, but at the same time to advertise you what we are going to do in the future. So gives you kind of mixed impression. So you studied differential equations for sure, and it will be not so hard to imagine. So if you have a one-order autonomous differential equation, I recall you that it's such a case when you have a map from Rn to Rn. In the course, you typically worked with two-dimensional case, and the word autonomous means that there is no dependence on time, on t. It only depended on x. Then there is a way, okay, you want it to be continuously differentiable. There is a way to define a flow using this equation. And that, you remember, the flow is what we defined when we gave a formal definition of the dynamical systems in a continuous time case. So for each x, there was a unique ft of x that started at x at time 0, and defined for all t in some neighborhood of 0. Assume that the solution is defined for all t. It's not always the case, because f can be ugly. But for instance, if, say, f is bounded, you can get it. So if it is defined for all t, then you apply the fact that the equation is autonomous, and you can be sure that ft plus s is ft of fs. The composition is the same as the addition of the time. And so it's enough to say that ft is necessarily a flow, because this map will be a C1 diffeomorphism of Rn. And conversely, it's also true that if you are given a flow, then you can define the map Tx to ft of x, and then you can simply write the equation. You can construct the equation by yourself, saying that the derivative of x is d dt, t equal to 0, ft of x. For example, it works very well when you deal with a linear autonomous equation, because you can consider x, it will be a matrix. That's what we've already mentioned when we were talking about the toral diffeomorphism. So you take these, and in this case, your ft of x, I hope you still remember, that is given by the exponent of a matrix A. So in this case, you get a flow. So you already studied many dynamical systems when you were studying differential equations. And probably the last example for today is the one that comes from the Hamiltonian mechanics. You also study, probably you study more Lagrangian mechanics as a part of your upbringing, but next step would be a Hamiltonian one. Maybe you heard already this word in physics. So this also gives you an example of dynamical systems as well. So this is example number 6. It's the one that comes from Hamiltonian system. So the flow is defined by a system that QE derivative is a partial derivative, and PI and UI can live different life between 1 and n. So it's a smooth Hamiltonian system function. And since the divergence is equal to 0, the flow preserves volume. You can construct a form like that, and this volume will be preserved by your flow. So you have a candidate, a natural candidate for the invariant measure, actually. And then maybe you also heard what the first integral is, the course of differential equations. And so the first integral is simply the function which is constant on the orbit of your dynamical systems. So if you deal with the Hamiltonian systems, there is a natural first integral, which is h. And since it's a first integral, then its level function surfaces are all invariant under the flow. And we easily can see the finite density smooth measure due to these two observations. So finalizing what we were talking about now, is that we already studied a few dynamical systems in other courses, basic courses of mathematics, but we did not think about them, that how they could be related. But in reality, very often, for instance, due to symbolic dynamics, there is a way to reveal this connection. And the goal for our further study of this course is to get familiar with those dynamical systems that are useful in other branches of mathematics, to study them using the techniques that we discussed already and with some others, and then to apply the results we have to the questions that arise and generated these systems. Okay, I think I have to stop here for today, actually. Just one technical question. I switched to Russian, I think, at this moment. Значит, обычно я делаю Google группу для курса, ну и туда выкладываю все подряд. Все подряд — это значит ссылку на видео лекции, плюс листочки, плюс, например, свои заметки. Я их сканирую. Если у меня есть время, я что-то техаю. Если его нету, то они лежат в рукописном виде. Вот. Насколько это удобно, если это будет Google группа? Просто это, мне кажется, ну, там будет Google группа, в нее надо будет вступить. Вот, и в ней будут, соответственно, приходить анонсы, и потом мы будем использовать ее, когда вы будете делать доклады, для того, чтобы сказать, что вот такого числа такой человек расскажет о том-то. Вот, то есть для анонсов тоже. Если это удобно, то я просто ее сотворю. Вы мне напишите, что вы будете ходить, а я сотворю и вас позову в эту группу, и, соответственно, там будут жить все. Материал. Что, Сергей Константинович, наверное, на сегодня мы на этом закончим, да? Потому что для первого раза все-таки 3 часа это, наверное, перебор.